And Monte Carlo means for me I can do parallelization. So I mean I parallelized, well, Victor split it up into pieces, and he told me these are the blocks, and then I just kept them together. I mean I just put them back together using that Swift tool, and we got this 20 times speed up on 4-dimensional, which was good. So when you build your model, if you think in terms of how I'm going to organize it into pieces such that somebody later will parallelize those pieces, it's going to buy you a lot. If you just if you design your model in a monolithical way, which is not easily split into pieces, you're not going to be able to take advantage of all this competition. So really, what we saw here that just this Monte Carlo shock spin, it's a very good example for, it's a very good case for parallelizing applications and using all these high performance resources. So this is the actual workflow that, so essentially Victor got the model from wherever he got it from, 1000, split it up into things that made sense, like this is the policy function computation, and then these are simulations for those households with shocks. So each of these is a simulation of the household over the 17 years, and then we run all the simulation in parallel. So here I'm just showing you what that Swift tool generating automatically this graph. So I wrote the dependency for us, which is like this much. Well, like we had the pieces from Victor, and then the workflow, the Swift tool just generated automatically this workflow and ran it for me, and I didn't even have to worry about what comes first and next and all that. It just ran it for me, I got the outputs, and I'm just showing here some cases of doing structural estimation for this model. This model has 5 dimensions, I think. Victor split into 5 dimensions, so I was doing 3-dimensional parameter sweeps because they were taking way too long. So just doing one of these took me probably about 8 hours, and that's 3 dimensions out of 5 dimensions rule in this actually doing the computation for them. So each one point I think took 10-15 minutes. So essentially you need a lot of computation power, and these tools allow you to automatically take advantage of the existing resources. So what they do is they run things for you. You define things properly and they run them for you. So you go away for a week, and then when you come back you have the US economy fixed. So the third example is, well, this is more like a bit childish from my perspective, but maybe it's useful for you. There is this other LEB model which deals with occupation choice. And we were running the model in simulation mode, and essentially we were trying to feed, to properly provide automatic inputs to the model such that the researcher can browse to the data source. So these TIE surveys that Townsend has collected over the years, it's a huge amount of data. It's like, I don't know, I would say 1 gigabyte of data just in this CDB. It's huge. It's thousands of variables. So how can you run this occupational choice at various disaggregation levels, or with various inputs, various variables as inputs? This occupational choice model takes as inputs some proxy for wealth, some proxy for credit, and a proxy for business or entrepreneurship thinking. So how do you build those proxies such that you can run the model and see what happens when you change the variables, or when you change how you build the proxy? So that's what this work is about. And build a nice interface to it, and like you choose the variables for the proxies, and you click run, and you're going to end up with a map result, with the result put on the map for each state or county, whatever disaggregation level you choose for running this model. And just the diagram of how I automate all this thing, essentially, just want to point out that I had like 12 different steps to actually extract data, format it for the MATLAB model, make that run. It was a very extensive process to actually automate data extraction, feeding to the model, and closing the loop by making some visualization and representation of the results. Last and least, the big computational tasks. Structural estimation, I mean, this is really big. There's some ongoing work, which I should start working on, but I haven't yet. Esteban Puentes, who just graduated last year, has this borrowing model. He's looking at ways of borrowing from banks, lenders, self-finance. And he runs into a problem, fact that the structural estimation part has to deal with a computationally intensive function. So it takes really long time for him to do that. And I'm going to show you how. I'm going to show you in the next page the actual representation of it. But essentially, the problem is that currently he uses MATLAB, right? He uses fmincon, and then fmincon objective functions as his expressive function, and that takes a lot. And he kind of needs to break away from evaluating that expressive function, and he needs to speed it up. So I said, okay, I can parallelize the function because the structure of the function allows me to parallelize it, but I can parallelize it outside MATLAB, not inside. So we are looking at ways of how to connect back that externally parallelized and sped up function to the solver, which does the maximum likelihood estimation procedure, which is part of MATLAB, fmincon in this case. So that's the problem that I should be working on soon. And also, like I said, for those of you who have dynamic programming cases for your models, like Ken Judd pushes for these forward-looking economic models, and he keeps asking me to build up these examples and platforms of how to run these models in these high-performance platforms in parallel, hopefully. So